particles out of that, right? Unless the energy available is higher than the E equals mc squared of the electrons. Right. Because it has to make them in pairs. Okay.
The charge
to keep the charge. Yes, because it's plus and a minus.
Right.
And so an electron is the lightest physical particle. Right. So nothing's happening.
Lightest charged particle.
It's not happening around us right now.
Yeah, it's the lightest charged particle. So it has to talk the electromagnetic field.
There it is. That's why light coming from lights, it's not just making particles. It doesn't have enough energy.
Yep.
Right. But if X-rays start to come out of there, X-rays, high energy X-rays, you can pop electrons into existence. Is there stepping down? So they need something.
The energy of the field is big enough to create the electron and anti-electron, so it will pair produce them.
Microscopes are enabled by X-rays, creating them, and the wavelength of X-rays is so tiny that you can see any detail. It's tinier than the detail. You can't have resolution higher than the wavelength of what light uses to see it. Right.
Now, back to dark matter, just to finish this point.
This is a whole massive other layer cake. Yep. You're telling me that is the mass of the dark matter.
Well, the lightest supersymmetric particle would be stable, should be around us.
That's what
so maybe it's filling space.
Right.
And here's the beautiful thing. Here's a beautiful This will make sense. When you do the calculation of how much of this lightest supersymmetric particle should be left over since the Big Bang, it exactly matches what you need.
This one tough.
It comes in the right abundance. And yet we've not found it. That may be the wrong answer. So sometimes things that just seem so deeply compelling are wrong, but we don't know yet.
You know enough in the theory of these particles to predict how you should detect them.
Yes. Which is the lightest supersymmetric particle on the flavor of the supersymmetric theory you're looking at. But in any given version, yes, you know exactly how the particle interacts.
Okay, so now you have everybody's favorite flavor, the theorists, come out with their competing model, but still, they got to have one of these particles. Okay, so now I'm an experimentalist, and let me test for this one. I don't find it. Let me test for that one. I don't find it. It's not looking good.
Yeah, I agree.
Okay,
I agree.
Okay,
I agree. Like, when I was a student, it was almost a foregone conclusion that you just had to look for it, you'd find it. This is the dark matter. Your supersymmetry also solves other problems. It's both a hierarchy problem, it solves the dark matter problem. It's a beautiful idea that seems perhaps not to be right now. It's not fully ruled out yet, but that may be where we're going.
People always said, great tragedy in science, a beautiful theory of slaying thoughts and facts. How do you know that the audio version of the podcast actually puts the fans, the video? You can get that the podcast. And most other podcasts have multiple ways you can get all that is possible. I've not been the same since we had lunch months ago. And you explained to me, and I said it here, that there are ideas circulating that the fabric of space might be woven by wormholes that connect the virtual particle pairs that come in and out of existence. And that if they're connected by wormholes, rather than just some field, then the wormhole is an actual structural texture of the universe.
Yeah. That the other way.
I'm sorry. First of all, I need some weed to deal with this. Because if I'm trying to figure out what you just said, because it's so freaking, I mean, it really is just crazy.
Well, let's back up. The vacuum of space.
Right.
Is not a vacuum, right? Because quantum physics requires what?
There's all sorts of uncertainty, and that uncertainty means that there's fluctuations, and therefore there are particle-antiparticle pairs, there's energy fluctuations, and field fluctuations.
Right.
It's a roiling mess out there in empty space.
So there's no nothing.
Yeah.
There is no such thing as nothing.
That's what's uncertainty.
Right. There's truly nothing. We couldn't have uncertainty.
Yeah.
So with the uncertainty, there's, gives us the fact that we do have
virtual particles. Yes. We know that they pop in and out of the system. And what you're trying to,
I think it's not that we know that no denies it because it's completely consistent.
well, I take it to the plasma metaphor, where you actually put two metal plates in otherwise empty space. They should simply sit there. They're drawn together, and the best explanation is it's the virtual pairs of particles that you're fluctuating through.
Into what a Star Trek nightmare. Exactly how the place. Okay, and evacuate what's in between. And makes sense. That vacuum between us and then slowly losing together. Right. There is a point within which a whole other force kicks in.
That's right. And it's not the gravitational force. It's not the gravitational force. Rather, it's a force that comes from the Casimir field, which is basically when the 40 is when it was discovered. Okay. It's definitely deserved one. It's an imbalance between the fluctuations of uncertainty within the plates and the fluctuations of uncertainty outside the plates. And that imbalance
Brings the force together.
Yeah.
Okay. So that's how we get the particle in the back. Okay, so now, why what compels you to say wormhole rather than just a figure?
Well, because it really comes from the idea of quantum entanglement. What we find is that entanglement, which normally we think of as particle pairs, but now we're finding that the vacuum of space may be stitched together by the threads of quantum entanglement itself. So deep down within the substrate of reality, it may all be stitched together by quantum entanglement. And then other work shows us that quantum entanglement connecting two particles is just like a wormhole, right, going from one to the other.
Because what happens in one happens to the other instantly.
Yes.
And that means they're touching each
They're
other
connected in some weird way. And entanglement is one language that we believe wormholes may be the general relativistic version of that.
I need to get lucky. Man, come on. Let's draw all yours.
Because we find mathematically, if we cut the threads of quantum entanglement, which we can do mathematically, space falls apart. It discretizes into little tiny pieces and it just disappears. I gotta go.
That leads you to the end of this. Don't leave me. Don't leave me. It's not just that there's a field there. It's the fact that they were quantum entangled that makes the wormhole model compelling.
Yeah, but I would say you don't even need the particle pairs. It's as if the entanglement is entangling regions of space. So space itself has a fundamental substrate woven by these threads of quantum connection. Now look, it's mathematical, but it comes out of our cutting-edge ideas. It all makes sense.
This makes sense. Right, okay, it's hard to know. Yeah, it works. And it started out saying the American, but what I love to know. Yeah, last thing.
Yeah.
Explain why you need more than 4 dimensions for your string theory universe.
Well, it's a very concrete explanation. When we look at the equations of string theory, there's a consistency equation where something must equal 0 and that doesn't work. That something is a product of two things. One term is really complicated, it's never 0. The other term is the number of dimensions minus 1. The only way to get it to be equal to 0 is for d to be equal to 10. That's it, I'm not joking. This is where the constraint of extra dimensions comes from in string theory.
The math is forcing our hands.
Forces your hand. And then you say, well, let me take this mass here. Then one thing you could say, well, if it's not e equals 4, 3 space and 1 time, throw the theory away. Others of us will say, hey, let's consider the possibilities. Yeah, exactly. So why should these 3 dimensions of space be the only one?
Right.
We only are aware of them because they're big enough that we can be directly aware of them with these really faulty sensors that we have.
Right. If it's only your sensors that limit that awareness, why not, in principle, can we build something that can gain access to these higher dimensions?
Yeah, so there are experiments on the table. Some have been carried out, but more precise ones may be done where you study Newton's law of gravity. Why does Newton's law go like 1 over r squared? Why do we teach our kids G and m over r squared? Geometric sphere in 3 dimensions of space. Yeah. Look at that sphere in 4 or 5 or 6 dimensions, and the 2 in Newton's law won't be a 2. No. It'll be a bigger number. The fall off will be differently. Right. And so look at the gravitational force on very small distances. Look for a deviation from the 1 over r squared that Isaac Newton told us about in the late 1600s.
Okay, that's only in our dimensional measurement. Okay.
Yes.
Okay, because I asked you again over that same.
Yeah.
Why do you we're not English? It's my annual fix with my annual Brian Grain infusion. It was dark matter, the ordinary matter with ordinary gravity in a parallel universe. Because for reasons I don't understand the math of the equation part, you were telling me that electromagnetic energy cannot escape our space-time, but gravity can.
In a certain model called the terrain universe, where our universe is membrane. Yeah, it's a membrane. So our universe is like a 4-dimensional membrane floating in a higher dimensional universe that might have other membranes.
Higher dimensional membrane.
Yes, and those other membranes like parallels, like 2 slices of bread and a big loaf of bread.
So one slice of bread is some other membrane or universe. Yeah. Ours is this one, but it's one multi-gravity. Yeah. Okay, and so gravity could leak out of one into the other.
Right. So so good. Yeah.
So if the other universe has 6 times, see, this is where you corrected me. Because I was thinking, because we have 6 times as much force of gravity operating in the universe as matter and energy can account for. So yes, factor of 6. Right. So I'm saying, why isn't it just a parallel universe that has 6 times the mass? And it's leakage into our universe, and we're trying to feel the elephant, trying to figure out what it is, but it's just regular matter in another universe whose gravity leaks. But then you said, if it's in another membrane, it's going to be dropping off faster than 1 over r squared. Yeah. Like 1 over r cubed. There's some higher dimension.
Yeah.
And if that's the case, it has to be way more than 6 times.
But you can imagine rigging it so that it would have the right amount.
Yeah.
And people have studied this, and it's hard to make these theories work in detail. But in principle, it's an idea that's actually worthy of investigating, because that's one way to make it invisible. Just put it in another
just stick it somewhere else. Exactly. And then where we can still calculate with it, there's not a problem.
Yeah. That's crazy. Over there.
All right.
I don't know what to believe about it. Nothing is real. Nothing is real.
Dark energy. I'm curious about this because it is a natural arithmetic element of Einstein's equation. It's like an integration constant, if I understood it.
Talk about the cosmological constant.
The cosmological constant in his equation that enabled Lemaitre to calculate that the universe is either expanding or, but the universe is not static. And so there's a term there. And if you've had calculus, you might remember there's a constant of integration. Often it's just 0 and you can ignore it. But when we were in graduate school, I'm a little older than you, when we were in graduate school, we always recognized, we paid homage to that constant that said that the sum is 0. If this term existed, it would mean there's a force operating in the universe opposite that of gravity.
Depending on the size of the cosmology.
Again. But if you would have either. Okay, well, I'd work with gravity again. Okay, but if you had a static universe, it would be something just holding up the universe against the blocks of gravity.
Which is why I'm saying.
And we don't have any reason to think it. So it could be 0. And we always have to go through that point. We say, here it is, we set it to 0 and move on. Yeah. Okay. Then it gets discovered. Okay, dark energy gets discovered in 1998, gets the Nobel Prize, using quantum physics, which has done so well by us. Perhaps the most successful theory ever about anything, fails in its attempt to predict the amount of dark energy in the universe. Yeah. And it fails badly by a factor.
What's up with that, Brian?
Of a Google.
Wow, by a factor of 10 to the 10 to
If I sent 123 or 100,
The Google's 10 and 100.
yeah.
It gets the wrong answer by the biggest amount ever in a mismatch between theory and observation.
Yeah.
So where are we with dark energy theory?
So look, what this is showing us is that quantum mechanics is incredibly successful when you apply it to the electromagnetic force, to the weak nuclear force, to the strong nuclear force. But we've long known that when you apply it to gravity, something goes wrong, something changes. This is the motivation for string theory, and this is the motivation for trying to go beyond conventional approaches. And so you're absolutely right. This is the clearest signal that something is wrong. Now, here's, I
But
think
that's not something that's wrong. That's actually a good thing.
well, it's an opportunity.
Yeah. Give me the opportunity. The press always says, "Oh, scientists are angry." No, we're delighted.
Yeah.
If something breaks, oh my gosh, it's a new thing.
That's right.
That's right.
And so I would say, my guess, where we're going is, and many of my colleagues agree with me, that it can't be quantified gravity. The way you have to quantize Faraday and Maxwell as electromagnetism, or the way you have to quantize the weak or strong nuclear forces. It may be that gravity and quantum mechanics are already so intimately connected that it's a completely different mindset when you approach them. You don't take the rules of quantum mechanics and slap them onto gravity. That gets you the wrong answer. That's the wrong approach. In fact, this idea of entanglement and wormholes suggests that gravity quantum already there. That makes sense.
You already have the chocolate and land.
And you exactly. So you just need to understand that melding better, and when you do, perhaps you'll be able to do a calculation with cosmological constant
That's
and get the right answer.
Right.
Now, another answer might be maybe the cosmological constant is not a constant. Right? There's recent maybe it's changing over time. And so you don't actually calculate the number, you just need to understand the dynamic of the process.
However, doesn't the math in general relativity require that to be constant?
No.
That's how it came out of the integral.
There can be a constant, but it doesn't have to be the only contribution that looks like that constant. And the other contribution is whatever time.
It can be a constant, but it doesn't have to look like, and then
It's not the only contribution to that term. Creating a field that slowly varies over time. And that field may dominate
there's a theory of matter to that equation.
Yes, it is related to that equation. Absolutely. So Einstein did not talk about that. You're right. And he did talk about the constant because you're right. It's just an integration between the two. It's right there.
Right. So the answer is scientific needs to modify, because that's how they reconcile this tension in the age of the universe.
Yeah.
Because the age of the universe is, in my day, universe, back to a truth. Now people are, I mean, it's 10% difference, so it's more than 6,000. Is what you're saying. Yeah, that's exactly what I'm saying. Yeah. But no. So, you relieve the tension, as we describe it, there's a 10%, it's some single-digit percent. Uncertainty in the age of the universe. Actually, not uncertainty. These two methods are very small type uncertainties that do not overlap. That's why everyone was freaking out. And as I learned recently, you can resolve that by allowing the cosmological constant to vary in some way. But that's a meta variation on top of
But this Hubble tension that people are struggling with today is actually something that also may point towards a dynamic of value. So we'll see. But yes, the true test of force and gravity that can fully understand the quantum mechanics included would be a calculation of the cosmological constant and get a number.
Are people smart enough to get this figured out?
I don't think so.
Oh, fuck. My last chance, man. I'm tired.
Because I told him, I said, look, Einstein came up with general relativity in 10 years by himself. You know, the string theorists is that dozens of you have been working on this for decades. Either you're all wrong, or you're all just too stupid to figure it out.
And it's probably a combination.
Love you, man, Brian. Thanks for coming back. That's right. Oh, good job, Sylvia. We'll find you in the hospital. That's good. You should be completely fried. That's fine. To take us out, let me remind us all, we are in my office at the 80th Anniversary American Museum of History, the Passive Creek. And after this conversation we just had, I delight in realize it and celebrate the fact that just a few pounds of organic matter inside of our head can not only contemplate, but figure out super important. And yes, we still have a long way to go. We don't know how long a way to go remains in front of us. But the distance we've come thus far gives us everything that we call civilization. And it's the power of mind over the mysteries of the universe. And that is a product of eternal curiosity expressed by our species, beginning in childhood, continuing for some into adulthood. That's how that exciting. We've never lost. So, I'd like to just give a shout out to our species.
Alright, I'm out. I ain't beating this. Getting beat up.